Welcome back to BugNoJutsu. In today's video, we're going to solve an interesting problem from LeetCode, called maximum average pass ratio. This is a greedy and heap-based problem that tests how well you can think about distributing resources optimally. We'll walk step by step through the problem statement, understand it with an example, break down the logic, and finally discuss time and space complexity along with some important insights. So stick around till the end, because this problem teaches a very powerful greedy pattern that you'll see again and again in competitive programming and interviews. Imagine a school that has multiple classes. Each class has a certain number of students, and we already know how many of them are guaranteed to pass. The rest might or might not pass. Now, the school has a few brilliant students in reserve, and these students are guaranteed to pass whichever class they are assigned to. The task is to assign these extra brilliant students across the classes in such a way that the average pass ratio of all classes is maximized. The pass ratio of a single class is simply the number of students passing divided by the total number of students in that class. The average pass ratio is just the average of all class ratios combined. What makes this tricky is that we can't just randomly assign the extra students. Each placement affects the ratios differently depending on the current class size and number of passing students. Our job is to carefully decide where to put these extra students to get the best overall result. Let's take an example. Suppose we have 3 classes. The first class has 1 student passing out of 2, the second class has 3 out of 5, and the third class has 2 out of 2. We also have 2 extra brilliant students to assign. At the beginning, the pass ratios are 0.5 for the first class, 0.6 for the second, and 1.0 for the third. Now, where should we put the extra students? If we add 1 student to the first class, its ratio improves from 0.5 to about 0.667. If we add 1 more, it improves further to 0.75. The second class, on the other hand, improves only slightly if we add a student, and the third class is already perfect with 100%. So the best choice is to give both students to the first class. That gives us final ratios of 0.75, 0.6, and 1.0. When averaged across all classes, we get about 0.783, which is the maximum possible. The key to solving this problem is realizing that each extra student does not increase all classes equally. Some classes benefit more than others when they receive a new student. To measure this, we calculate the gain, that is, the improvement in pass ratio if we give 1 extra student to a particular class. At every step, we want to assign the student to the class with the highest gain. To implement this efficiently, we use a heap data structure. A heap allows us to always pick the class with the largest gain in logarithmic time. Initially, we calculate the gain for every class and push these into the heap. Then, for each extra student, we pop the class with the best gain, assign the student, update that class's gain, and push it back into the heap. By repeating this process until all students are assigned, we ensure that we're always making the most optimal choice at each step. Finally, we calculate the average pass ratio across all the classes after distribution. The time complexity of this approach is n log n plus extra students times log n. The first part comes from building the heap with n classes, and the second part comes from distributing each of the extra students, where each push and pop operation takes log n time. The space complexity is n, since we're storing information about all the classes in the heap. The main insight here is that greedy works because the problem has an optimal substructure. If you always place a student in the class where they yield the largest improvement, you never regret that decision later. Another important takeaway is how heaps help us implement this strategy efficiently. This pattern, calculating a marginal gain and always picking the maximum, shows up in many allocation and optimization problems. So if you get comfortable with this style of thinking, you'll unlock solutions to a whole range of problems that at first glance may look unrelated. The maximum average pass ratio problem asks us to assign extra brilliant students to classes in a way that maximizes the overall average pass ratio. The trick is to always place a student where they give the highest improvement, which we calculate as a gain. Using a max heap, we efficiently pick the best class at every step, assign students, and compute the final average. This greedy plus heap approach ensures the optimal solution with n plus extra students, log n, time. And that's the solution to the maximum average pass ratio problem. I hope this breakdown made it easier for you to understand not just the answer, but also the reasoning behind it. If you found this helpful, don't forget to like the video, subscribe to BugNoJutsu, and hit the bell icon so you don't miss future uploads. I'll be back soon with more problems, detailed explanations, and tips to make you stronger in problem solving. Thanks for watching, and I'll see you in the next one.